Welcome everyone. I am Professor Kari Iowanu and I will be teaching Fundamentals of Light and Lasers this semester. You may see on this first slide that you see PALTECH listed here, and also you see the NSF symbol. PALTECH stands for Photonics and Light Technical Education Center, and that was funded by NSF grant number 1700564. For those of you who are not aware, the NSF is the National Science Foundation. Like I said, my name is Professor Kari Iowanu. My office is in T136, but since we are remote this semester, I'm not there, I'm home. Also, since we're remote, I give you my telephone number as 914-606-8561, but I am not able to access that number remotely. So if you want to get a hold of me, please use my email, which is my name, Kyriakos.Iowanu @sunywcc.edu. For this class, I have already posted a PDF of the text, which is called Fundamentals of Light and Lasers by Optech on Blackboard. Assignments and additional information will also be posted on Blackboard. I have actually asked for all of your addresses because while we are remote, a lab kit will be sent to your house so you guys could work on the labs from home. The topics that we will be covering this semester are the nature and properties of light, optical handling and positioning, light sources and laser safety, basic geometric optics, and basic physical optics, and then principles of lasers. I hope you found that video informative. I will be putting a link to that video in Blackboard so you could look at it directly instead of through this PowerPoint. And also for any other videos that are in this PowerPoint and the future PowerPoints, I will be including links to them in Blackboard for you guys to go and get them. So, photonics. What is photonics? Photonics is the science of light and photon generation, detection, and manipulation. Photonics are used in almost every field, and I guarantee you that everyone in this class uses photonics on a daily basis and may not even realize it. In such things as your cell phone, for one, your computer, for others, there's photonics pretty much everywhere. So I'm going to show you guys a short video about photonics, and then we will continue. I'm going to talk a little now about lasers. I know that everyone in this class has used a laser at some point, whether it's a laser pointer, whether it's the laser in an optical drive, such as a DVD or a Blu-ray player, or something like a tool. I know at home I have a laser level that I use when I'm working around the house. So I don't know if everybody knows what the word laser stands for. And what it stands for is light amplification by stimulated emission of radiation. Again, lasers are used in a lot of different things. So I have here a list which is not all inclusive, but just something to think about the next time you wonder, why are lasers so important? They're used in CDs, DVDs, Blu-rays. Even though I know those are starting to be phased out, they're still used in many applications. Fiber optics. Some of you may have fiber optics coming into your house to bring your internet service. Well, fiber optics rely on lasers to transmit data, and then data transmission is right there. Medicine. There are lasers used in medicine in a lot of ways. Among them, there's laser surgery. The LASIK eye surgery is entirely based on cutting with a laser. But there are many other applications where lasers are used. Cell phones. My cell phone, I know, actually has a laser that is used for the autofocus on the camera. Construction, I mentioned I have a laser level that I use around the house, but there's also professional grade laser levels and all sorts of equipment. Measurements, there are laser tape measures. Don't want to use the word tape measure on here, but they are used to measure a room or anything else by bouncing a laser and getting it back. And other measurements that we may not like that are done with lasers are the police actually use lasers to measure your speed. So how does a laser work? So in this picture, this is a gas laser. There are also solid state lasers, but this is a typical gas laser. And again, I have one that I could show you if I was in person, and I normally do, but because we're remote, this picture is going to have to do. So basically, the way a laser works is I have a flash tube, and I have a tube that is filled with some type of gas. And on the one side, I have a mirrored surface that's a 100% mirror. And on the other side, I have a partially mirrored surface, which is not 100%. So what happens with this laser is that that flash tube flashes and it excites the atoms that are in there, and the atoms move to a higher energy orbit. When they return to their normal state, so when they start to lose energy, they drop down to their normal state, they actually emit photons, which are particles of light. And so as the light is bouncing inside of that tube, it goes to the 100% mirror and then back to the 90. So 10% of that light is what is the output of our laser. And that's what we see when we shine a laser on something. So how is laser light different than other light that we see and use? Well, laser light is coherent and it is of one wavelength. So if you look at figure 1 here, you'll see what I mean by coherent, because all the waves line up right on top of each other. Whereas visible light that we see around us, it contains multiple wavelengths and it is not coherent. So if you look at there, the waves are not lined up. They're different wavelengths, so they are not coherent. So the properties of light that we're going to look at are the wavelength, the frequency, the period, the amplitude, the speed, the phase, the coherence, polarization, and energy. These two figures will show us the first 4 characteristics that we spoke about, or properties that we spoke about for light in the last slide: the wavelength, the period, the frequency, and the amplitude. So if you look at figure 1-1, you'll see it actually lists displacement versus distance along a wave at an instant in time. And in that, you'll see the displacement is basically the distance, the vertical distance measured from the equilibrium position of any point. The peak displacement is what's called the amplitude. So you could see that is defined on the right-hand side. It's called out on the right-hand side of the drawing, that I'm going from the neutral side to the highest point, and that's my amplitude. Then I could see that the wavelength is the distance over which the wave repeats itself. And it's from, in this one, from the crest of one wave to the crest of the other. or the peak of one wave to the peak of the other. They both should be the same. And it's written by the Greek letter lambda, which you'll see at the bottom of that. The second figure, figure 1.2, actually shows displacement versus time. And that capital T is what's called the period, and it tells us how long it takes for one wavelength to take and repeat itself. Then we also have something called the frequency, and the frequency of the waves is the number of cycles of the wave in 1 second, and is represented by the Greek letter nu, which looks like a little v, but that's the lowercase Greek letter nu. So these are ways that we will talk about a wave and a wave of light. So equations that we will use for them is that my frequency is equal to 1 over my period in seconds. Or I could rewrite that and say my period in seconds is 1 over my frequency. And the frequency is defined, is given in hertz, right? Now, you may have seen that number because it's used in various things. When we talk about sound waves, the human ear is capable of hearing sound from 20 to 20,000 hertz for normal young people. As we age, we lose certain frequencies of our hearing. Men tend to lose their higher frequencies, and women tend to lose the lower frequencies of their hearing. So that is where some place that you may see frequencies, but also when we look at something like a computer, CPUs are rated in their frequency. So working with more equations to define the to work with on here, since speed is defined as the distance traveled divided by elapsed time, the speed of a wave is the distance traveled in one cycle, the wavelength, divided by the time required for one cycle, the period. So the equations 1.3 and 1.4 are expressions for wave speed, which is v for velocity. So v is equal to my lambda, or divided by t, my period, or I could say it's equal to lambda times nu. And lambda is my wavelength, nu is my frequency, and t is my period of my wave. The speed of light traveling through a vacuum is 3 times 10 to the 8th meters per second, and is expressed by the symbol c, which can be substituted for v in equation 1.4 to give equations 1.5, 1.6, and 1.7 from our textbook. So c is equal to lambda times nu. It's also, I could rewrite that and say lambda is equal to c over nu, and nu is equal to c over lambda. So in there I had the 10 to the 8th. So I'd like to go over these because we use these quite often, and you should all know the prefixes that are used to form units for wavelength, time, frequency. So the table is also in our textbook. It's on page 8 of the textbook. So if you see a capital T, that stands for tera, and that is 10 to the 12th. So in frequency, you might see something given in terahertz. And then G, the capital G, is giga, which is 10 to the 9th. And again, an example in frequency, you might see something given in gigahertz. And then M is mega, 10 to the 6th, and you might see megahertz. or you might see in the K, the little k is kilo, which is 10 to the third or 1,000. So you might see a frequency in kilohertz. And I mentioned before that human hearing, the normal range is from 20 to 20,000 hertz, or you might see that written as 20 to 20 kilohertz, 20 hertz to 20 kilohertz. Then if I look at a little m stands for milli, which is 10 to the minus third, and in wavelength you might see that as a millimeter, or as a distance you might measure it as a millimeter, or in time a millisecond. So that's 1/1000th of a second is a millisecond. And then micro is given by the Greek letter mu, and that is 10 to the minus 6. And you'll see either a micrometer or just micro, or a microsecond. And then a nano is given as the little letter n, and it's 10 to the minus 9th. So you can measure something in nanometers or nanoseconds. And then pico is 10 to the minus 12th, and you can measure time in picoseconds, which is 10 to the minus 9. So I know at least one of my students in this class has taken my Intro to Nanotechnology class in the past. So, as you see, for a nanometer is 10 to the minus 9th meters. And in that class, we actually talk about stuff on the nano scale, stuff that's really, really small. So this figure here shows the wavelength of light and the frequency of light. And our light is in the electromagnetic spectrum, as it's called. So if you look at the top chart, you'll see that light is a very small part of that spectrum. And then as we go higher in the chart, we have our ultraviolet, X-ray, gamma ray, and lower we have infrared, microwave, radio, and TV. And then if you look at the middle drawing, you'll see that light fits inside in between the infrared and the ultraviolet. And from there, we'll see the different colors of light that are their frequencies and wavelengths are in there. So as you could see, if I have a frequency of 4.3 times 10 to the 14th, we're dealing with a deep red. And then as we go to 7.5 to 10 to the 14th, we have violet. And in between, we have the red, orange, yellow, green, blue, blue, and violet. So we'll talk a little about the index of refraction. The first lab, when you get your lab kits, will actually have to do with the index of refraction. So the speed of light in a vacuum is approximately 3 times 10 to the 8th meters per second. The speed is reduced when it's traveling through optical material. The index of refraction of a material is the ratio of the speed of light in a vacuum to the speed of light in that material, and is expressed with the following equation, where n is equal to c over v. So n is the index of refraction, v is the speed of light through the medium, and c is the speed of light in a vacuum. So the frequency of a light wave does not change when it enters a material, but its wavelength does. So the index of refraction can also be written as n is equal to lambda O over lambda M, or the wavelength in a vacuum over the wavelength in the material. So this is shown in this slide, where we see in air we have our lambda O, and then once it hits that optical material, the wavelength changes and is actually smaller. So in this case, they're telling us that our lambda in the material is actually 2/3 of the original lambda, which gives us that the index of refraction for that material is 1.5. So I'm going to just go through an example, and like I said, the first lab that you'll do once you get your lab kits will be a lab on index of refraction. So here we're given that a helium neon laser, which has a wavelength of 633 nanometers, travels through a glass window of a refractive index of 1.65. It says find the speed and the wavelength inside the glass. So if we rearrange the previous equation that we had, where we had that n is equal to c over v, I could rearrange that and I could say v is equal to c over n. And we know that the speed of light, c, in the vacuum is 3 times 10 to the 8th meters per second. That was given on the previous slide. And I divide that by my index of refraction of 1.65, which we're given in this problem. And we see that the velocity in that optical material, that glass, is 1.82 times 10 to the 8th meters per second. And similarly, if I take my equation of 1.9, which says that my index of refraction is my wavelength in the vacuum over the wavelength in the material, and I rearrange that, I could say that the wavelength in the material is equal to the wavelength in the vacuum divided by my index of refraction. So I will see there that I take the 633 nanometers and I divide it by 1.65, and I say that my wavelength in my material in this piece of glass that we're given here is 384 nanometers. So the next topic we'll talk about is the phase of a wave, right? So the wave phase. So if I look at figure 1.6 from our textbook, which is given on the slide here, I could say that the equation for a sine wave is y is equal to a times the sine of alpha, where y is the vertical displacement, either positive or negative, above or below the midline, which in this drawing is AB. And a is my amplitude, or my maximum displacement, and alpha is the phase angle or angular displacement from 0 degrees. Now, I included the textbook, a PDF of the textbook, and when I scanned this figure in, it actually, the way I had to do it, it says need help in graphing on the bottom. And in your textbook, and this is on page 14 of your textbook, there are links with a lot of these things to videos. And I would suggest that you look at these videos for a little extra help with these topics. These were done by Optech, who also wrote the textbook, and they're very helpful in helping you guys get a better understanding of these topics. So after watching this video and after reading, I would suggest clicking on these videos and watching them. So here I could see my waves are, I have wave 1 and wave 2, right? So on wave 1, point A has a phase of 90 degrees and point B has a phase of 270 degrees. Therefore, the 2 points on wave 1 are said to be 180 degrees out of phase. So that's the 270 degrees minus 90. The same principle applied at point C on wave 2 to determine the phase difference between wave 1 and wave 2. So the phase angle at point A on wave 1 is 90. The phase angle on the corresponding point C on wave 2 is 180. Thus, the phase difference is 90 degrees, and the two waves are said to be out of phase by 90 degrees. So early on in this presentation, I talked about coherent light. And if you see the upper figure 1.8a in this drawing, in this slide, you'll see that each of the 5 waves has the same phase angle, alpha, along the vertical line YY, and they all have the same wavelength. So that is how I could see this is coherent light now. They're all at the same phase. They're all at the same, have the same wavelength. If I look at B, you can see that there's 4 waves there, and each of those curves has a different wavelength. Their phases are different along that vertical line. So that would actually be how incoherent light looks. Now we're going to talk a little about the polarization of light. And polarization of light refers to the orientation or direction of vibration of the electric field as the wave propagates through space. Following terms commonly are used to describe polarized light. So unpolarized light has no specific orientation of electric field. The direction of the electric field varies randomly at approximately the frequency of light. In figure 1.9a of our textbook, you could see this. This randomness is depicted by the electric field having several different orientations. Plane polarized light is light in which the electric field oscillates in one plane only. And this is shown on figure 1.9b and c in our textbook. Horizontally polarized light, the plane that contains the electric field is horizontal, perpendicular to the plane of the paper, as pictured in the head-on view. In vertically polarized light, the plane of the electric field is vertical, up and down, in the plane of the paper as shown with vertical arrows. In circularly polarized light, the direction of the electric field is neither random nor confined to a single plane. The direction of the electric field of circularly polarized light sweeps out of a circle during each period of the wave. So here is the figure showing us the unpolarized light at the top, horizontally polarized light in the middle, and vertically polarized light on the bottom. Now, I hope that everyone here is aware, but there are certain things that we use every day that are polarized. One thing that is very popular, by the way, are polarized sunglasses. And by having polarized sunglasses, there's actually slits that are cut into the material of the sunglass. And what that does is it blocks the light that is coming in at the different angles. Similarly, your LCD screens that we use for watching our computers, our phones, and the like, those are also polarized. And one thing you can do to see what I'm talking about is if you have a set of polarized sunglasses, rotate the sunglasses in front of the screen and you'll see how the image gets darker or even completely gone. It's completely blocked as you turn those sunglasses. So here we have an optical element turn. A linear polarizer consists of a plastic sheet that contains needle-shaped crystals of an iodine compound. These crystals strongly absorb the horizontal components depicted in figure 110, but they transmit most of the vertical components. Thus, after passing through the linear polarizer, unpolarized light emerges as linearly polarized light, and in this instance in the vertical direction.